Good morning, everyone. I hope you can all hear me. Well, yeah, I'm gonna talk about an algorithm or a way how to solve large-scale semi-definite optimization problems. And I will have one particular application, but I just do hope that this technique can be applied to polynomial optimization as well, or at least to some relaxations in polynomial optimization. Okay, so what do I understand by large-scale SDP? In SDP, we actually have several different dimensions. So here is my SDP, and we have the size of the variable. So in this case, the variable is a vector, so we have this n. Then we also have the size of my LMI, and we have a number of LMIs. Of course, it can be put in one big LMI, but software would never treat it like that. So I assume that we have these three dimensions, n, m, and p. Now, what is good and what is bad for majority of SDP software, and now I'm talking basically about interior point methods, about software based on interior point methods, or perhaps augmented Lagrangian method as well. So what is bad if we have many variables and a big matrix, a large matrix inequality? Then every software has troubles with that, and why is that? We will see on the next slide. The case when n is large and n is small and m is large is relatively rare, and so I just didn't investigate that too much. What is good for interior point software is that if we have a large number of variables, or many variables, and relative to this large number, small matrix constraints. And it turns out it doesn't really matter if we have many of these small matrix constraints. So if P is large, it is still a good situation. Why is that? If we have a look at complexity of an interior point method, or in one iteration of the interior point method, so what is the bottleneck of that is the solution of a linear system with a matrix H, which either is full or it's sparse. That depends on the application. And it's usually called a Shor complement matrix. Now, what is costly is first the assembly of that matrix, the computation of this matrix, and then the solution of the linear system with this matrix. The solution of the system is typically done by Cholesky factorization. So, sorry, if my matrix is full, then it's just n cubed. Again, n is the number of variables. So the matrix H is n by n matrix. And the complexity of the assembly of H, well, it depends on all my three dimensions. But assuming, now this is the bad case when n is more or less the same as m, so we have many variables and large matrix inequalities, then we have this ugly quartic complexity. So this will be the dominant factor, the assembly of the matrix, which will be much more costly than the actual solution of the system by Cholesky factorization. Sorry. On the other hand, if n gets bigger than m, then let's say if it's comparable to square of m, then this step, the assembly, is about as costly, about as expensive as the solution of the system. And if n is much bigger than m, then the solution of the system becomes the dominant part in the complexity. And the situation is even more clear in a case when the matrix is sparse, when this matrix H is sparse. Then, okay, the Cholesky factorization, again, it only depends on the size of the matrix, but also on the sparsity structure of that matrix. So I just have some so some alpha there, which is a number between 1 for diagonal matrix and 3 for full matrix. So typically it's something about around 2. And then the complexity of the Hessian assembly, of the Schur complement assembly, we don't have anymore this dominating factor there. So still, if n is about the same size as m, then we still have this huge complexity. So now it's even much more costly than the Cholesky factorization for sparse matrices. But now if n becomes bigger and bigger than m, then this number is becoming smaller much faster than in the dense case. So for this case, we have the complexity which is smaller than quadratic. Okay, so I will return to this green table in a second, but we may first ask, so what can we do to get rid, so knowing this complexity of interior point method, how can we solve very large SDP problems? So, well, in case when n is much larger than m, actually this should not be there, then we have seen that the Hessian, the solution of that system, so the Cholesky factorization here or there, is becoming the dominant factor. It is more costly than the assembly of the matrix. And then, okay, we can try to solve, instead of using Cholesky factorization, we can try to solve that system iteratively. And this is done in one version of the software SDPT3. It's done in our software, Pen SDP. Jacek Gonjo is looking at similar thing as well. And this is also an advertisement for the talk of my ESR, Sude Habibi. She will talk about this approach next week in the continuation of this workshop. We can also, of course, use different algorithms. We are not forced to use interior point method. We can use bundle algorithm. We can use the approach of Sambuer and Renato Monteiro. We can use ADMM. We can use augmented Lagrangian. We can use optimization on manifolds if we have more information, like let's say low rank of the matrices. But we can also try to use the interior point method, but to reformulate the bad problems as equivalently as a good problem. So we can try to change the formulation of the original problem and then again use the interior point method. So looking again at the complexity, and now just assuming that my matrix H is a sparse matrix, so that's this green table, then we see that the bad case indeed is the case when n is about the same size as m. So the number of variables, the size of this variable vector is about the same as the size, as the dimension of my LMI. And the good case is this case here, that n is much, much larger than m. And we will see that in a typical situation, we will be able to go from this triple of variable of dimensions. So this is n, m, and p. So going from one big matrix inequality with many variables, we will be able to reduce it to reformulate the problem as a problem of this size. So kind of many more variables, but not really many more, 5 times more variables, but much, much smaller matrix variable, linear matrix inequality. And P, the number of matrix inequalities, will grow. But we will see from that formula that this is still sort of harmless number compared to this n to power 4. So from the complexity point of view, this should be much better situation than that. So how can we reformulate a problem with this type of dimension as a problem, equivalent problem with these dimensions. And I'm going to introduce two approaches to that. So that was like an introduction, why do we need the decomposition? And I'm going to introduce two approaches. One is a kind of well-known approach, at least in the SDP community, which I'm calling Chordal decomposition of the matrix. And I will try to show that it can actually be even improved for this part of application which I will be using. And the other type of decomposition will be new. I will assume special structure of the matrix, arrow type matrices, and then in that case we will see we can get rid of the Chordal decomposition of that assumption of chordality. So what is the Chordal decomposition? I need to introduce a little bit more notation because it's based on a graph representation of matrix sparsity. So what is graph representation of matrix sparsity? So assume we have a sparse matrix A, and we will want this matrix to be positive semidefinite. So the sparsity graph of that matrix, that's simple. It's simple and undirected, unweighted graph which has an edge between the two vertices. Vertices correspond to the numbering of my matrix. There is an edge between vertices I and j if and only if there is a non-zero element in the aij position of the matrix. So if there is a 0 in ij, there is no edge between vertices I and j. That's simple. And here are two well-known facts about sparsity graph. The first one is that the sparsity graph is Chordal if and only if Cholesky factorization of my matrix A, perhaps under some perturbation, has a 0 fill-in. So there is no fill-in the Cholesky factorization of the matrix, if and only if the sparsity graph is a Chordal graph. And the other fact is that the cliques in the sparsity graph, they correspond to dense submatrices in my matrix A. So in particular, the maximal cliques in the graph correspond to the maximal dense submatrices. And here's a typical example. So I have a matrix like that. The crosses mean potential non-zeros. The rest are zeros. Here is the sparsity graph corresponding to that matrix. And okay, here, this is one of the two maximal cliques in that graph, which corresponds exactly to this dense submatrix. And there is another dense submatrix corresponding to another maximal clique in that graph. Two more examples of typical matrices with Chordal sparsity graph, and those are also typical examples of matrices with 0 fill-in of Cholesky factorization. The first one is a 5-diagonal matrix. We have this nice graph, and clearly the maximal cliques are these triangles here, this one, that one, corresponding to these dense submatrices, this one, 3 by 3 dense submatrices. The other example is this, we can call it arrow type matrix, and the corresponding sparsity graph is in here. And again, this is a Chordal graph, and the maximal cliques are these triangles, this one, that one, corresponding to again 3 by 3 matrices, because now the matrix is it's this matrix with these additional elements. So this is one of those 3 by 3 matrices corresponding to the maximal cliques here. Now, an example of a sparse matrix which has a non-Gödel sparsity graph is in here. And okay, we don't see much from that matrix, but we can see a lot from the graph. It's a nice kind of regular graph. It is not a Gödel graph. Why is that? We can find a cycle of length 4, which does not have any thought. And here is that cycle. 1, 2, 3, 4. So it's a cycle of length 4, and there is no chord. So we would need chord like that or like that. So what we can do, we can extend that graph to make it chordal. So we can extend it by these red edges, assuming that there is indeed an edge in the graph between these 2 points, which means we assume that these elements, which are assumed to be 0, are actually non-zero, potentially non-zero, these elements of that sparse matrix. So this is something I would call Gödel extension. And we can do it, of course, for any graph. So in the worst case, we will finish with completely full matrix, where we will connect all possible, all existing vertices in the graph. Now, the Gödel extension, or the Gödel decomposition of positive semidefinite matrices, it was introduced in SDP by the group of Masakazu Kojima in that paper. Actually, I think it was introduced before 2011, but it's nicely summarized in that paper. And it is based on one single theorem, which was actually independently proved by two groups of authors, one group from optimization, one from the graph theory, both in the 80s. And you can read all that in this nice book/paper by Lieven Vanderberg and Martin Anderson as well. So what is this theorem saying? It says that, okay, we assume that we have a graph, we know its maximal cliques, and it's a graph which is a sparsity graph of certain matrix. Now, the theorem says that this graph is Gödel if and only if every matrix A, which is positive semidefinite, and which has sparsity graph G, so the matrix A has a sparsity graph G, so this matrix is positive semidefinite, and it can be, so if it is positive semidefinite, then it can be written as a sum of positive semidefinite matrices, of P's positive semidefinite matrices Y. P is the number of maximal cliques, and these matrices Y, K, are only non-zero on these maximal cliques. So in a way, these may be much smaller matrices, if I just consider the non-zeros in those matrices. So I can say that A is a sum, my say big matrix A is a sum of smaller matrices which are positive semidefinite and which are only non-zero on the maximal cliques of that Gödel graph. Now, from the point of view of semidefinite optimization, this means that a constraint, an LMI, with that matrix A can be replaced by a number of smaller constraints, smaller LMIs, with some so far unknown matrices YK, which sum up into my matrix A. So here is a small example. Looking again at the first example from the talk, I have these two dense submatrices in my sparse matrix. I have two maximal cliques, this one and that one. So I can look at that as a matrix with two overlapping blocks. And in this case, Y1 would only be non-zero here. Y2 would only be non-zero in the blue elements. So P would be equal to 2. So here is that situation. This is my red matrix. This is the blue matrix. And the theorem says that a positive semidefinite matrix K, the whole matrix, can be written as a sum of a matrix Y1, which is only non-zero there, and Y2, which is only non-zero here. Now, of course, these Y1 and Y2 are unknown, but and the other fact is that these red matrices, they are not positive semidefinite. So in this case, K is K1 plus K2, but K1 and K2 are not positive semidefinite. So what we are trying to find, we will try to find a matrix Y1 and Y2, which will be positive semidefinite and which will sum up into K. Now, clearly, because, for instance, the matrix Y2 is a zero in zeros in this position, and because this part of the submatrix plus this part of that submatrix Y1 should be equal to those elements or to that submatrix of the original matrix K, and clearly this part of Y1 must be the same like K111. The same for this matrix or this matrix. So the only unknown part of the matrix Y1, for which we know that it exists, is this part on the overlap of these two dense submatrices. And because we know that this overlap is equal to K122 plus K222, then we need to introduce just a single additional matrix variable, let's call it S, and we have to add it to the red matrix and subtract it from the blue matrix, such that this plus that gives me the same, which is in this green rectangle. Okay, so we need to introduce a dense submatrix, a new variable, and then instead of this matrix inequality, we have two smaller matrix inequalities saying that this matrix is positive semidefinite, that matrix is positive semidefinite, but we have this new additional matrix variable S. Now, there is a nice corollary to that theorem. Assume again that we have this matrix A, which is a sparse matrix. It has a sparsity graph G, and the nodes or the vertices of that graph are simple numbers 1 to n, the dimension of the matrix. So let's call it set n. Let's call it set capital N. And now, of course, we can partition the set into overlapping subsets I1 to IP. In the third decomposition, these would correspond to the maximal cliques, but let's forget for the moment the maximal cliques. Let's just say we partition it somehow into these sets, and we assume that these sets are overlapping, so we can define some A, K, K plus 1. Those are the overlaps of the two subsequent set I, K. Now, we further assume that our sparse matrix is a sum of matrices, of P matrices AK, which are only non-zero on those index sets IK. Then the immediate corollary of the theorem says that the matrix is positive semidefinite if and only if it can be written as a sum of matrices A tilde, where A tilde is constructed from AK, this is AK, minus and plus some matrix S, which are only non-zero on these intersections, on these overlapping sets. So we have additional variables, matrix variables, non-zero, only on those overlapping sets. And okay, these matrices are then, so these additional variables, they guarantee that this matrix A tilde is a positive semidefinite matrix. Which means now we can choose the partitioning of the set 1 to n. We are not really bounded to the maximal cliques of the original, which are used in the original problem, in the original theorem. So, for instance, looking at these 5 diagonal matrix, using the original theorem, we would find the maximal cliques, which are these triangles, and the overlaps, they would correspond to these 2 by 2 matrices. So we would have to introduce how many? 5 additional 2 by 2 matrices corresponding to the overlaps of the maximal cliques, of the maximal dense submatrices. But using the corollary, we can say, okay, let's just split that set into 2 subsets. So let's assume that the maximal clique is actually that. So there are some fictitious chords there. So assuming that actually there are some, that these elements are potentially non-zeros. And in this case, we get, instead of decomposition into 6 maximal cliques, so instead of 5 additional variables, 2 by 2 matrices, we only get 1 additional variable, 2 by 2 matrix, which will be this one. Okay, so we can sort of extend the maximal cliques. So in particular, when we know the sparsity structure of the matrix, we can choose a regular partitioning. So we don't have to rely on some automatic extension of a non-Gödel matrix into a Gödel matrix. We can choose a regular extension, regular partitioning of that matrix. We will see it in the application in a few minutes. Okay, so that was the Gödel decomposition. What are the drawbacks of that? And I've said this is not really new. Perhaps that corollary is a little new, but it's based on a well-known theorem. What is the drawback of these? There are 2 drawbacks. The first one, that we still need to rely on an underlying Gödel extension of the graph. So if the sparsity graph is not Gödel, we still need to extend it to a Gödel graph. So we need to introduce many potentially many non-zeros in our sparse matrix. For instance, if we have a matrix looking like that, then the sparsity graph of that matrix is this nice, let's say, wheel. And if we decide to partition the set of indices into 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6 subsets, index subsets, we would get 5 additional matrix variables of dimension 4 by 4. So these would correspond to the overlaps. I don't know if I can zoom on this. Yes, to the overlaps. So the additional variable, for instance, would be this matrix together with that matrix together with that matrix. All that would be 4 by 4, one of those 4 by 4 additional matrix variable. So in particular, we see that we need to assume that actually there is a non-zero, there are non-zeros at the positions where originally there were zeros. So for the additional variables, we need to assume that there are non-zeros here. In order to satisfy the correlated assumption, then instead of the original sparsity graph, we will get such a Gödel extension, much denser graph. and the corresponding dense matrix would be, or denser matrix would be looking like that. So that's one drawback, the existence, the need for the Gödel extension. And the other drawback is that we need these additional variables, and these must be full. And potentially for big problems, we may need many additional matrix variables, and maybe not so small additional matrix variables. So this may add to the, still add to the complexity of interior point method, and it can add to the memory requirements of the interior point method. So the question is, can we do better? And I don't have much time to explain that. In fact, we can do better. We can improve both of these drawbacks here by introducing additional structure into our sparse matrix. And by that, we can get rid of the Gödel assumption, and we can improve the complexity of those dense submatrices. So again, for the arrow matrices, I assume that we split the set of indices into some subsets, which have non-zero intersections, so there's non-zero overlap. Again, I assume that my matrix M is a sum of matrices Mk, which are only non-zero on these overlaps. But in particular, I assume that the matrix M or Mk has a structure, that its upper left part is only non-zero on Ik, and that this is a vector. Actually, it can also be a narrow matrix, but for the sake of simplicity, I assume that this is a vector, which again is only non-zero on the index set Ik. And then we have an additional matrix, which is actually only non-zero at this tail, or the point of the arrow. So I would call that arrow type matrix. And I will assume that, okay, this is a sparse matrix, or okay, some of those matrices AK is a sparse matrix. And additionally, I assume, and this is what I have to pay for getting rid of the Gödel assumption. I need to assume that the sum of those matrices AK is positive definite. And then I can claim that, or we can prove that this matrix M is positive semidefinite if and only if there are additional vectors which are only non-zero on those intersections, on those overlaps, such that the matrix M is a sum of some matrices M tilde, and those matrices are again constructed from the original matrix Mk, from that tip of the arrow, and from those additional or using those additional vectors, again only non-zeros on the intersections. So if we compare this to that corollary, we had a very similar claim, but here we had full matrices, full additional matrix variables Sk. Now we only have vectors. So the matrices, the additional matrices, are replaced by vectors, or in other words, the additional matrix variables are actually just rank 1 variables using this assumption about arrow type matrix. Now, looking back at my example with this wheel sparsity graph, for the Gödel, using the Gödel decomposition, we had this Gödel extension. Now, using the arrow decomposition, using that theorem for arrow type matrices, we had that extension of that graph, which is sparser than this one, and which actually is not Gödel. We don't need the Gödelity of the underlying graph. So actually the matrix, the extended matrix for the arrow decomposition can be much sparser than for the using the Gödel decomposition theorem. So in particular for this example, using the Gödel decomposition, we would have 5 additional matrix variables of dimension 4 by 4. Using the arrow decomposition, we only have 6, well, we have 6, but vector variables of dimension 3. And of course, for bigger examples, the difference between this and that will become much bigger. The question is, okay, can we use that at all? So are there any applications? Are there any applications which lead to these arrow-type matrices with that additional assumption of positive definiteness of this upper left part of the matrix? And the answer is yes, there is at least one important application, which is called Topology Optimization. It's an application from mechanical engineering. And in here, we try to design a mechanical structure. Imagine we want to design a bridge like that, which is fixed here on the banks and which is subject to, let's say, one load or many other loads. The typical result of that would be a figure like that, where in this figure every pixel corresponds to a single variable. The variable, you can think of it, is like a thickness of the material at that single point. It's not actually a point, it's a small rectangle. So naturally we get very many variables because we want to have as many pixels in the final figure as possible. And this problem can be formulated, I will not go into the modeling, but it can be formulated as a semi-definite optimization problem. Again, the variable is rho, corresponding to every finite element. So the number of variables is the number of finite elements. And we have one big LMI here. And the size of this LMI, that's the number of nodes in the finite element discretization multiplied by the dimension, by 2 or by 3, the space dimension of the structure. So in particular, we can see that, and of course, this is the matrix K depends linearly on the variable rho. So in particular, we see that in this application, we have many variables, the number of finite elements, so rho is of large dimension, and we have one large matrix inequality of dimension, say, n plus 1, where n is the number of nodes times the spatial dimension. Okay, the question is, can we replace that by several smaller matrix, smaller LMIs? And for that, we have to look at the sparsity graph of our matrix K. And the nice thing here is that the sparsity graph of the matrix is completely determined by the finite element discretization. So, for instance, if I have a structure like that, or domain like that, a rectangle, this would be the finite element discretization by 8 finite elements. Then the sparsity graph of the corresponding matrix, so this is the corresponding matrix K of rho. The sparsity graph is this graph here. We know that graph. It is not a Gödel graph, but it can be extended to a Gödel graph. But in particular, because of course, we know at the beginning what the finite element discretization looks like, what is the finite element mesh. So we can always partition the, let's go in here. So if we have a finite element discretization, we can always partition it just as we like. Either we can split it into 2 subdomains, just like in domain decomposition, in 4 subdomains, in more and more subdomains. It's just our choice. Simply every subdomain should include at least one finite element or more. So this is exactly that splitting of the index set I was talking about. Now we can really do it manually. We can do it as we like. And then we can use this, either the Horler decomposition. For instance, if we just split the finite element or the graph into two subdomains, we will get two matrices, just like before, the red one and the blue one, plus the additional row and column. But we can also use the arrow decomposition, because this matrix is exactly of that arrow structure. From finite element theory, that matrix is always positive definite, actually positive semi-definite, but for this application it's positive definite. And we have this additional row and column, which have the right non-zero structure. So we can use both decomposition, the Horler decomposition or the arrow decomposition. How do they compare? So now we have LMIs, we solve them by MOSEC. Here's a comparison of the Horler decomposition and the arrow decomposition for a particular examples, which is discretized by 40 by 20 finite elements. So we have 800 finite elements, which means that in the original problem with one matrix inequality, we have 801 variables. The size of that LMI, the size of the matrix is 1600, so they are of the same order. MOSEC needs 70 iterations or 69 iterations and about 1000 seconds of CPU time. Now, if we decompose using the Horler decomposition, if we decompose the graph into 8 maximal cliques or fictitious maximal cliques, then, so 8 subdomains, then we will get many more variables, because we have the additional variables corresponding to the dense submatrices on the intersections. But the matrix size will be much smaller, and the result is that we only need 31 seconds. And if we go further with the decomposition, so if we decompose the original mesh into 200 subdomains, so we will get 200 matrix variables, 200 LMIs instead of one. We will get many, many more variables, but very small LMIs, 19 by 19 matrices. And the result is that we go from 1000 seconds only to 7 seconds when we solve it by MOSEC. Now, using the arrow decomposition, we can do even better. In particular, we will get much less additional variables, because instead of dense matrices, we only have dense small vectors. Of course, the decomposition, the size of those matrix of those LMIs will be the same, but the time is at least a little shorter than for the Horler decomposition. But this difference will be bigger for bigger examples. This is a bigger example now with 7,200 variables, much bigger LMI. The original problem, I was unable to solve it by MOSEC because it simply didn't fit into memory. But if I just extrapolate the CPU time from smaller examples, it would take like 6 days to solve it. Now, using the Horler decomposition, we may go down to 100 seconds, but using the arrow decomposition, we can go down to 42 seconds to solve the decomposed problem. And of course, if we can solve it in 42 seconds, we can still increase the dimension. So this is my last slide. So this table presents a number of problems of the same type, but of increasing finite element discretization. So in the end, the largest problem is 160 by 80 finite elements. In the original formulation of the problem, the LMI would have 1200 variables, and the matrix constraint would be 26,000 by 26,000. Impossible to solve by MOSEC. The extrapolated CPU time would be like 81 days. But if we solve the decomposed problems where each subdomain only contains 4 finite elements using the arrow decomposition, so the matrix size of all matrices would be just 19 by 19, then you see, even for the bigger problem, we can solve the biggest problems in a little bit more than 1 minute. And for me, the most important information is the complexity. So if you look at the complexity of MOSEC for the original problem, so on the dependence on the CPU time on the size of the problem, we will get complexity, we will get this parameter of about between 3.5, which corresponds to the theoretical complexity of interior point method. For the decomposed problem, we get just linear complexity, which was quite surprising for me, and of course, that's quite nice to see. Okay, so that's the arrow type decomposition, and that's the end. Thank you for your attention.